Welcome to MAT307 numerical analysis class. In this lecture, we are going to continue our discussion on numerical differentiation. We will first start with an approximation to the second derivative of function, namely central difference. We consider Taylor series expansion of f of x naught minus h and f of x naught plus h around x naught. When we do that, the first one, the first Taylor series approximation for f of x naught plus h will look like this, and for f of x naught minus h will be this one. If we add these two equations, we will obtain on the right hand side f of x naught plus h plus f of x naught minus h. So this will be our left hand side. On the right hand side, we see if we add these two, we will basically cancel these two terms, and then these two terms will remain, and this two term will cancel out, and this will also remain. So we will end up with this formulation here. Okay, so if we solve this expression for the second derivative of f at x naught, this will give us this equality. Okay, with this equality, we can introduce central difference formula for the second derivative. So this is the second derivative, and we will approximate the second derivative by this formulation, and then say this will be the error due to the central difference formula. Okay, so the second derivative will be approximated by this formula here, and the error due to this approximation will be this quantity. So this will be basically h squared times the fourth derivative of f at some point c, which is between x naught minus h and x naught plus h, and this will be divided by 12. Okay, the theorem for the error due to central difference formula. So we will find an error bound for the central difference formula. For that, we assume the function f is four times continuously differentiable function, and we also assume that the fourth derivative attains its maximum m on the interval x naught minus h to x naught plus h. So on this interval, our fourth derivative, the fourth derivative of the function f, will be attaining the maximum value m. So mathematically, we can rewrite this phrase like this equality. So m is equal to the maximum of the fourth derivative in absolute value, and x is varying from x naught minus h to x naught plus h. So this m is the maximum value of the fourth derivative. If this is the case, we say the c is between this interval. So the fourth derivative of f at c is less than or equal to m, because m is the maximum value. So we say the error is this quantity, so h squared times the fourth derivative of f at some c divided by 12. So this is bounded by m. So we see the error has to be bounded by h squared times m divided by 12. So this is an upper bound for the error with the central difference formula. Okay, so a remark: if we know the maximum value, or if we can have an idea or prediction for the fourth derivative of the function on the interval x naught minus h to the x naught plus h, then we can control the error by scaling h values. If we know m, then we can choose our h value so that it will the error will remain within a certain value, or less than some certain value, some certain tolerance. Okay, an example. Find central difference approximation of the second derivative of fx is equal to x cube at x not equals 1. And we take h is equal to 0.1 and h is equal to 0.05. And then we compute errors and upper bounds, find upper bounds for the errors for each h values. So let's start with h equals 0.1. When we use this quantity and the values of f, this is indeed the central difference formula for x not equals 1. And if we substitute h.1 here, we will obtain f of 0.9 minus twice the function value f value at 1 and plus f value at 1.1 divided by h squared, which is 0.1 squared. And then if we substitute all these values in the function formulation and obtain the results, after some arithmetics, we will obtain the second derivative is approximated by 6. If we do the same computations for h equals 0.05, then these steps are the same except on the value of h. Then we will still obtain the value x for the approximation of the second derivative. The exact value of the second derivative at x not equals 1 is needed for the accuracy analysis. So if we take the second derivative of x cubed, this will be 6x. And when we substitute 1 for x naught, we will obtain the second derivative is equal to 6. Basically, this was supposed to be double prime because we are interested in finding the second derivative. So this is this double prime. So there's a typo here. Okay, let's continue with this. The second derivative is equal to 6, and what we found for second derivative with two h values will be also 6. So it seems like the exact value of the second derivative is found for both these h values. What could be the reason for this results? So we have exact values for the approximations. What might be the reason for that? To answer this question, we need to investigate the upper bound for the error. The error with the central difference formula is basically this. So we need to find the fourth derivative of the function to see what's happening with in the upper bound of the upper bound for the error. So if we take the fourth derivative of x cubed, we obtain 0 basically. When we substitute the 0 here, this will be like the upper bound for the error is equal to 0. So error must be bounded by 0. So error is a non-negative number. So non-negative number is bounded by 0 means the number itself is 0. So error has to be equal to 0. Because this is true, we obtain the exact value because the fourth derivative of the function is equal to 0. If we instead work with, for example, instead of working with x cubed, if we were to work with, for example, x to the fifth, then the fourth derivative wouldn't be 0 anymore. So this will give us some error besides 0. Okay, some alternative approaches for the first derivative are given in this given below. So the first derivative can be also found by this formulation. If we use this formulation, the first formulation, we obtain the h squared accuracy. So with this formulation, if we use this formulation for the first derivative, this will give us fourth order of accuracy. So we have h to the 4 for the error. So these are the error terms, this and that. This part will correspond to the formulation, the approximation, and this part will be the approximation, and these are the errors. So for the third one, if we use this part, so starting from here to there, so if we use this formulation, still we obtain the accuracy of fourth order. So here C1, C2, C3 are between, for example, here in the first approximation, between x naught minus 2h to x naught. So C1 is in this interval, and C2 will be between x naught minus 2h to x naught plus 2h. So this is where C2 lives, and C3 will be between x naught and x naught plus 4h. So these are the values of these are the intervals where the C values are in. Okay, an example: the derivative of the function f of x is equal to x to the x can be found by logarithmic derivative, as the derivative is equal to ln x plus 1 times x to the x. So this is the analytical derivative value. So find the numerical derivatives of f of x at x naught is equal to 1 with the given approximations above. So we have given 3 approximations, and we will use these approximations to approximate the derivative of f at x naught equals 1. And we take h is equal to 0.1 and h is equal to 0.05 to compute errors and perform this approximations, find approximations. Okay, so let's start with the first approximation. So the first approximation is this one. So if we work with h is equal to 0.1, the first approximation will be indeed we just substitute the values of the function and h on the formulation, nothing else. So here, if we do that, we see the error is equal to 0.0081. And if we do the same for h is equal to 0.05, then the error will be this quantity. And you see the h value is indeed halved. So 0.05 is the half of 0.01. So when we halve the h values, the error will be about 1/4 of the original error. So taking half of the h will give us 1/4 of the error. So this is because the approximation itself is second order. Okay, with the second approximation, we if we do the computations with h is equal to 0.1, we obtained error is this quantity, and for h is equal to 0.05, the error will be this quantity. If we compare errors, when h is halved, the error will be around 1/60 approximately. This is something we expect because the second approximation here, the second approximation is fourth order. So if we take the half of h, the error will be 1/16 times the original error, assuming this is the constant. Okay, so the error will be 1/16 approximately if we compare this to. With the last approximation, if we choose h is equal to 0.1, this will be the error, and h is equal to 0.05, this will be the second error. If you compare these two errors, we see halving h values will reduce the error by 1/21 approximately. But what we expect was with this approximation, this is still fourth order, so what we expect is 1/16, but in this case we see the error is reduced approximately by 1/21. Okay, with this last approximation, we expect the reduction on the error by a factor of 1/16 when the value of h is halved. However, computations show the reduction of 1/21 is that. Next, we define h one more time to investigate this phenomenon. What's going on? So if we take the half of h one more time and perform the computations, we see this is the derivative value, and the error will be this much. If we compare this error with the previous error, so with this error, we also see the if we halve the h value, the error will be 1 over 19 approximately. So 1 over 21, 1 over 90. Okay, the expected error with the last approximation explains this phenomenon, because as you see, if when we refine h values, when we take the half of h values, the approximation is the reduction on the error was 1 over 21 and 1 over 19. It seems like it's going to 1 over 16, but it's going from going with very good approximations. So we obtain very good approximations up until some point, and from some point on, when we reduce h values, this will be around 1 over 16. So this is what we expect. Thus, we can guess that the fifth derivative of the function is decreasing very fast on the interval. So the error with the third approximation was this quantity, and here we have two terms, the h term and the fifth derivative of the function. Okay, so the fifth derivative of the function on this interval, indeed. So it seems like if this is not if we don't see 1 over 16 here, it seems like there is something going on with the fifth derivative. Okay, so if this is not doing what it's supposed to do, there must be something happening with this function, this fifth derivative. Okay, so here this explanation says the error depends on the value of the fifth derivative as well as the value of h. Thus we can guess that the fifth derivative of the function decreases very fast on the interval from 1 to 1 plus 4h. As the value of h decreases, we also shrink this interval. So this means the contribution of the fifth derivative also decreases. So it shouldn't be surprising for us that the results are more accurate than expected, because the function, the fifth derivative of the function, is decreasing very fast on this interval. Similarly, for a given function whose fifth derivative is decreasing very rapidly on this interval, these rates should be less than 1 over 16. Okay, so this is something we expect. So we say this for this sort of convergence, like the asymptotic convergence. Okay, so in the asymptotic regime, it's converging to 1 over 16, but in reality, it is not identical to 1 over 16. Okay. Nevertheless, these rates are expected to approach 1 over 16 with the refinement of h values, because when we refine h values, this interval will shrink, and the decrease in the on this interval, decrease of the fifth derivative on this interval will not have much contribution on the error. So this will the error will the convergence, or the rate of the errors will be approaching to 1 over 16 in the limiting case. Okay. Next, we talk about round of errors in the numerical derivatives. We have only considered truncation error of the model so far, so we only we use Tyler series expansion, and then we truncate the expansion at some point and say, okay, this is the truncation error, and we obtain this much error out of these approximations. However, if we perform our computations on a machine with absolute accuracy, we will also observe some errors with run of the operation with the operations of the machine. Okay, and also the numbers on the machines won't be exact, so there will be some sort of errors at that point as well. So if we perform our computations on a machine with epsilon accuracy, the relation of a number x naught to its representative on the machine will be x naught bar is in this form. So this is from the very beginning of the course. So x naught will be equal to its representation on the machine plus epsilon times the magnitude of x naught. Okay. Similarly, there will be epsilon 1 and epsilon 2. These are both less than epsilon, the machine epsilon, such that the function value at x naught will be equal to function value, the representation of the function value on the machine plus epsilon 1 times the function value of f. And also here we will see the function value of x naught bar plus h bar will be also equal to the machine representation of this operation plus epsilon times the function value itself. Okay, so these are something we know. If we consider forward difference formula, for example, we can do the same for the other methods as well. If we consider forward difference formula, we basically find the error between the derivative and the machine representation of this derivative. So here, if we substitute the approximation for this, that will be f prime x naught bar minus the approximation for that. So this is the what we use for to approximate the first derivative. So we just put its equal here for the forward difference formula. Okay, so we take the difference. When we do that, we can also rewrite these two function values in terms of their equals. So these two, if we substitute them here, these two values in this formulation, we obtain this equality. Okay, so here we break the fraction. So we put epsilons together, and f values will be together. So we will rewrite this as two fraction. So the first fraction will be this, and the second fraction will be that. Okay, and using the triangle inequality, we see this part in absolute value plus that part will be greater than the original absolute value. So this will be less than that, less than or equal to that. Okay, so in this part we see the approximation with forward difference formula, and we know this is this much accurate, 1 over 2 times h times the maximum value of the function, the second derivative of the function at some point here. Okay, so this is from the central difference formula. From here we can we know epsilon 1 and epsilon 2 are less than epsilon, so we can bound this by epsilon times function values, the difference of function values. We can apply the triangle inequality one more time, and this will give us twice the function values, right? So if we have some maximum value for the function value on this interval, then this will be twice the function value. So we will have 2 times epsilon divided by h, this h will come out, times the maximum value of the functions. Okay, so this is triangle inequality used with the maximum value of f and using this inequalities. Okay, so we obtain this. Okay, what we have with this, so remark, the total error in computing the derivative on an epsilon accurate machine will be in this form. So this is the error bound for the derivative. Okay, if we check this part, this is due to the truncation error, and this is due to the runoff error. Okay, therefore As the value of h decreases, the error decreases thanks to the first term. So thanks to this term, as h decreases, this part will decrease, but it will increase due to that term. Okay, this is also expected because if h decreases, then the number of operations will increase, so the run of error will increase. Okay, so this will be the part where the error is decreasing, and with this error will be increasing if h decreases. In general, the number epsilon is very small comparing to h values. So h values will be quite large comparing to epsilon. So the first term dominates until h is too small. For example, if we have h is much greater than the root of epsilon, then the error will be dominated by this term. So error will be approximated by this term. Okay? And if the error is close to that term, that means the if h value decreases, error will decrease. Okay, so given we are on this part, so if we have h is much greater than root of epsilon. If h is chosen too small, if h is less than root epsilon, then this part will be dominating. Okay, this part will be the dominating error part for this approximation. So that will be the approximation for the error. Okay, so if h is chosen too small, then decreasing h will increase the error. Okay, so as a result, it seems like we have a graph of the error like this. So error versus, so say this is the graph of error versus h values. Okay, so this is h and this is error. The error will decrease until some point here. This point will be root epsilon. Okay, until we arrive at h is equal to root epsilon, the error will decrease, and from that point on, error will increase. Okay, so we observe that the optimum value of the error will be obtained when h is approximately equal to root of epsilon, the machine epsilon. From this point on, the smaller h values will be, the smaller the h is, the more the error will be. Okay, so as in this graph, we see from that point on, if h is less than epsilon, then our error will start increasing. So this is not h, this is 1 over h. Let's put it here right. Okay, so okay, that's all for this lecture. We are pretty much done with the derivatives. So thanks for watching carefully.